Imagine standing at the edge of an infinite ocean. But this isn't Earth. The water stretches endlessly in every direction, deeper than our deepest trenches, warmer than our hottest seas. Above you, a sky thick with hydrogen gas glows with an alien hue. The air, if you could call it that, would crush human lungs instantly. Yet, in this hostile, otherworldly environment, something extraordinary might be stirring, something that changes everything we thought we knew about life in the universe. On September 11, 2023, NASA's James Webb Space Telescope detected a molecule in the atmosphere of a distant world called K2-18b. That molecule was dimethyl sulfide, DMS. On Earth, DMS is produced almost exclusively by living organisms. Phytoplankton in our oceans release it. It's a signature of biological activity. And now, 120 light-years away, orbiting a cool red dwarf star, we've found it again. This is the story of K2-18b, a Hycean world that might harbor the first evidence of alien life. For decades, humanity's search for life beyond Earth focused on one template: planets like ours. We called them Goldilocks worlds, rocky, temperate, with liquid water on the surface. Earth became the blueprint, Mars with its ancient riverbeds, Europa with its subsurface ocean, Enceladus with geysers shooting water into space. These were our prime targets, but they all shared one thing: they resembled Earth in fundamental ways. Then, in 2021, astronomer Niku Madhusudan from the University of Cambridge proposed something revolutionary. What if we were looking in the wrong places? What if life didn't need rocky ground or a thin atmosphere? What if it could thrive in conditions wildly different from our own? He introduced the concept of Hycean worlds, planets covered entirely by deep, warm oceans with thick, hydrogen-rich atmospheres. These worlds orbit red dwarf stars, the most common type of star in the galaxy. They're larger than Earth, between 1.6 and 2.6 times our planet's radius. They're tidally locked, meaning one side always faces their star, and they're everywhere. K2-18b was discovered in 2015 by NASA's Kepler Space Telescope during its K2 mission. It orbits within the habitable zone of K2-18, a red dwarf star in the constellation Leo. The planet is about 8.6 times more massive than Earth and roughly 2.6 times wider. Early observations suggested it had water vapor in its atmosphere, but scientists couldn't determine if it was a mini Neptune, a gas-rich world with no surface, or something else entirely. For years, K2-18b remained an enigma, a world caught between categories. That uncertainty ended when Webb observed K2-18b in 2023. Webb launched on December 25, 2021, and became operational in July 2022. Unlike Hubble, which observes primarily invisible light, Webb specializes in infrared wavelengths. This allows it to peer through cosmic dust, analyze distant atmospheres, and detect molecules that older telescopes simply couldn't see. When Webb observed K2-18b in 2023, it didn't just confirm water vapor, it found methane, carbon dioxide, and something unexpected. To understand why K2-18b matters, we need to grasp what makes Hycean worlds unique. Unlike Earth, which has a thin nitrogen-oxygen atmosphere and shallow oceans covering 70% of the surface, Hycean worlds are entirely oceanic. Their oceans aren't just deep, they could extend hundreds of kilometers down, far deeper than Earth's Mariana Trench. The pressure at these depths would be immense, potentially thousands of times greater than at Earth's sea level. Yet, life on Earth has shown us that extreme pressure is not a barrier. We've found organisms thriving at the bottom of our deepest ocean trenches in conditions we once thought impossible. The atmosphere of a Hycean world is dominated by hydrogen and helium, remnants from the planet's formation. These atmospheres are thick, extending thousands of kilometers into space. The greenhouse effect on such worlds would be powerful, trapping heat and maintaining liquid water even at relatively distant orbits from their stars. The temperature range for Hycean habitability could span from below freezing to over 200 degrees Celsius, depending on depth and atmospheric pressure. But here's where it gets fascinating. On Earth, life requires a stable environment with the right chemical ingredients: water, carbon, nitrogen, phosphorus, sulfur, and trace elements. Hycean worlds have all of these. Their oceans would contain dissolved gases from the atmosphere, including carbon dioxide and methane, both essential for carbon-based chemistry. The interaction between the ocean and atmosphere would create dynamic chemical cycles, much like Earth's carbon and nitrogen cycles, but on a vastly larger scale. Dimethyl sulfide is the key piece of the puzzle. On Earth, DMS is produced by phytoplankton, microscopic algae that form the base of the marine web food. When these organisms break down, they release sulfur compounds, including DMS. It's so prevalent that you can smell it near the ocean. That characteristic sea breeze odor is partly DMS. In Earth's atmosphere, DMS plays a role in cloud formation, affecting our climate. Importantly, there's no known non-biological process that produces significant amounts of DMS in a planetary atmosphere. Volcanic activity can release sulfur compounds, but not DMS specifically. Chemical reactions in the atmosphere can create trace amounts, but not at detectable levels across interstellar distances. This is why the detection on K2-18b is monumental. If DMS is there, and if it follows the same rules as on Earth, then something on K2-18b is producing it biologically. That something could be analogous to our phytoplankton, organisms living in the upper layers of that vast alien ocean, harnessing energy from their star, metabolizing sulfur compounds, and releasing DMS as a byproduct. The James Webb Space Telescope observed K2-18b using its near-infrared spectrograph, NIRS-PEC, in transmission spectroscopy mode. When K2-18b passes in front of its star, an event called a transit, starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths of light, creating a unique spectral fingerprint. By analyzing this fingerprint, scientists can determine the atmosphere's composition. The team, led by Nikku Madhusudhan, conducted 2 separate observations in 2023. The data was painstakingly analyzed over several months. The first results confirmed earlier findings. Water vapor and methane were present in significant quantities. Carbon dioxide was also detected, consistent with a carbon-rich atmosphere interacting with a water ocean. But then, buried in the spectral lines, something unusual appeared. At a wavelength around 2.7 micrometers, there was an absorption feature that didn't match methane, water, or carbon dioxide. The team ran simulations, testing every known atmospheric molecule. The match was dimethyl sulfide. The signal wasn't overwhelming, it was tentative, requiring careful statistical analysis to confirm it wasn't noise or contamination from other molecules. But it was there. Madhusudhan and his colleagues were cautious. In science, extraordinary claims require extraordinary evidence. The detection of DMS on an exoplanet 120 light-years away was exactly that, an extraordinary claim. They published their findings in the Astrophysical Journal Letters on September 11, 2023, stating that DMS was a candidate biomarker, but emphasizing the need for further observations to confirm it. The scientific community reacted with a mix of excitement and skepticism. Some researchers praised the rigor of the analysis, noting that Webb's instruments were specifically designed for this kind of detection. Others pointed out potential sources of error. Could the signal be due to instrumental artifacts? Could it be a different molecule with a similar spectral signature? Could non-biological processes on K2-18b produce DMS through unknown chemical pathways? NASA issued a statement urging caution. While the detection was intriguing, they emphasized that it was preliminary. Independent teams would need to analyze the same data and conduct new observations to verify the finding. The agency made it clear this was not a confirmed detection of alien life. It was a tantalizing clue that required further investigation. Yet the implications were impossible to ignore. If confirmed, this would be the first time humanity had detected a potential biosignature on a world beyond our solar system. Not on Mars, where we've searched for decades, not on Europa or Enceladus, where we plan future missions, but on a world so alien, so different from Earth, that we barely imagined it existed a few years ago. The data from Webb didn't just reveal DMS, it painted a comprehensive picture of K2-18b's atmosphere. The methane levels were particularly noteworthy. On a hydrogen-rich mini-Neptune, methane should be depleted by photochemical reactions driven by the star's radiation. But on K2-18b, methane was abundant. This suggested something was replenishing it, either geological activity or biological processes. On Earth, methane is produced both geologically, through volcanic activity and hydrothermal vents, and biologically, through microbes called methanogens. The presence of carbon dioxide alongside methane is also significant. These two molecules together indicate active carbon chemistry. On Earth, the carbon cycle involves the exchange of carbon between the atmosphere, oceans, and living organisms. Plants absorb carbon dioxide during photosynthesis. Marine organisms build shells from dissolved carbon. When they die, they sink to the ocean floor, sequestering carbon for millions of years. On K2-18b, a similar cycle could be at play, but on a planetary scale never seen before. The team also noted the absence of ammonia. In hydrogen-rich atmospheres, ammonia should be present if the atmosphere is in chemical equilibrium. Its absence suggests either active chemistry that destroys ammonia or specific formation conditions that prevented its accumulation. This detail, while subtle, supports the Hycean model. It suggests K2-18b isn't just a bloated mini-Neptune, but a distinct type of world with a complex atmospheric composition. Madhusudan's team ran climate models to simulate K2-18b's environment. They found that with a hydrogen atmosphere and a liquid water ocean, the planet could maintain habitable surface temperatures despite receiving far less stellar radiation than Earth. The greenhouse effect from hydrogen and methane would trap enough heat to keep the ocean from freezing. The models also suggested that the ocean could be hundreds of kilometers deep, potentially creating distinct thermal layers with varying habitability zones. The scientific community began debating follow-up strategies. Webb could observe K2-18b again, using different instruments to confirm the DMS detection and search for additional biomarkers. Other telescopes, like the upcoming Extremely Large Telescope, ELT, and the Habitable Worlds Observatory, could provide complementary data. Some researchers proposed looking for oxygen or ozone, though these are less likely on a hydrogen-rich world. Others suggested searching for phosphine, another potential biosignature, or analyzing seasonal variations that might indicate biological cycles. Meanwhile, the public reaction was immediate and electric. News outlets around the world ran headlines, "NASA finds signs of life," "Alien ocean world discovered," "Are we alone? New evidence says no." The excitement was palpable, even as scientists repeatedly urged caution. The detection of DMS on K2-18b forces us to reconsider our assumptions about life's requirements. For centuries, we've believed life needs certain conditions: moderate temperatures, liquid water, a rocky surface, protection from radiation. Hycean worlds challenge this. K2-18b receives intense radiation from its red dwarf star, especially during stellar flares common to these stars. Yet, a thick hydrogen atmosphere could shield the ocean below. The water itself would absorb much of the remaining radiation, creating a protected zone at depth where life could potentially thrive. One of the most compelling aspects of Hycean worlds is their sheer abundance. Red dwarf stars make up about 70% of all stars in the Milky Way. Many of these stars host planets in their habitable zones. If even a fraction of these planets are Hycean worlds, and if a fraction of those harbor life, the implications for the prevalence of life in the universe are staggering. We could be living in a galaxy teeming with alien oceans, each one a potential cradle of biology. But let's address the elephant in the room. Could something other than life produce DMS on K2-18b? This question is essential to evaluating the discovery. On Earth, abiotic or non-biological production of DMS is minimal. Volcanic gases contain sulfur compounds like sulfur dioxide and hydrogen sulfide, but not DMS. Industrial processes can create DMS, but those obviously don't apply here. Some chemical models suggest that under extreme conditions, high pressure, specific catalysts, DMS could form abiotically. However, no natural abiotic source has been identified on Earth that produces DMS in detectable atmospheric quantities. On K2-18b, the conditions are extreme. The pressure at the ocean-atmosphere interface could reach several bars, significantly higher than Earth's sea level pressure. Chemical reactions in such environments could potentially produce unexpected compounds. Some scientists have proposed that ultraviolet radiation from K2-18's flares could drive photochemical reactions in the atmosphere, creating DMS from methane and sulfur compounds. This remains speculative and would require laboratory experiments to test. Another consideration is the stability of DMS in a hydrogen-rich atmosphere. DMS can react with hydrogen, breaking down into simpler molecules. If DMS is present in detectable amounts, something must be continuously producing it to replenish what's lost to chemical reactions. This is consistent with biological activity, which would constantly generate DMS as organisms metabolize. The discovery also raises questions about the origin of life on K2-18b. If life exists there, did it originate independently, or could it have been seeded by panspermia, the transfer of life between planets or even star systems via comets or asteroids? Given K2-18b's distance from Earth, panspermia seems unlikely unless life is far more widespread and resilient than we imagine. More probable is that life arose independently, suggesting that the conditions for abiogenesis, the origin of life from non-living matter, are more common than we thought. The scientific debate around K2-18b highlights a fundamental challenge in astrobiology. How do we interpret ambiguous data? Dr. Sarah Seeger, an astrophysicist at MIT and a leading expert in exoplanet atmospheres, has emphasized that biosignatures must be considered in context. A single molecule, even one like DMS, isn't definitive proof of life. We need to detect multiple biosignatures, understand the planet's full chemistry, and rule out abiotic explanations. Dr. Lisa Kaltenegger, director of the Carl Sagan Institute at Cornell University, has pointed out that Hycean worlds represent a paradigm shift. "We've spent decades looking for Earth 2.0, she said in a recent interview, but maybe we should be looking for Earth 0.5 or Earth 3.0, worlds that are habitable in ways we never imagined." K2-18b could be the first of many such worlds. Skeptics, however, remain unconvinced. Dr. Joshua Chrysanson-Totten, a planetary scientist, has argued that the DMS signal could be a false positive, possibly caused by overlapping spectral lines from other molecules or noise in the data. He advocates for independent confirmation using different instruments and observing techniques. Then there's the question of what life on K2-18b would actually look like. If organisms exist there, they would be fundamentally adapted to conditions unlike anything on Earth. They might be single-celled, analogous to our bacteria or archaea. They could exist at various depths, from the upper layers to the frigid high-pressure depths. They might metabolize hydrogen, methane, or sulfur compounds. They might not photosynthesize at all, instead deriving energy from chemical reactions, a process called chemosynthesis, common in Earth's deep-sea hydrothermal vent communities. The discovery has also sparked philosophical discussions. If life exists on K2-18b, it would be the second known origin of life in the universe. This would strongly suggest that life is not a cosmic fluke, but a natural outcome of planetary chemistry under the right conditions.
So here's the question I want you to think about. If we confirm that K2-18b harbors life, what would that mean for humanity's place in the universe? Would it change the way you see our planet, our purpose? Drop your thoughts in the comments. I'm genuinely curious to hear what you think. And if you're finding this as mind-blowing as I am, hit that like button. It genuinely helps this video reach more people who are just as fascinated by the cosmos as you are. This discovery is massive, and the more people who understand it, the better we can collectively process what might be the most important scientific finding in history. Now, let's dive into what comes next, because this story is far from over. The detection of DMS on K2-18b is just the beginning. NASA and the European Space Agency have already scheduled additional observations with the James Webb Space Telescope. These observations will use different filters and longer exposure times to confirm the DMS signal and search for other molecules. Specifically, scientists are looking for dimethyl sulfoxide, DMSO, another sulfur compound produced by marine organisms on Earth, and carbonyl sulfide, OCS, which could indicate volcanic or biological activity. Beyond Webb, the next generation of telescopes will revolutionize our ability to study Hycean worlds. The Extremely Large Telescope, ELT, currently under construction in Chile, will have a mirror 39 meters in diameter, nearly 4 times larger than any existing optical telescope. It will be capable of directly imaging some exoplanets and analyzing their atmospheres with unprecedented detail. The Habitable Worlds Observatory, a NASA mission planned for the 2040s, will specifically target potentially habitable planets, including Hycean worlds, searching for multiple biosignatures simultaneously. Closer to home, missions to Europa and Enceladus will test technologies for detecting life in subsurface oceans. If we find life in our own solar system, it would lend credibility to the idea that ocean worlds, whether icy moons or Hycean planets, are prime habitats for biology. There's also a push for laboratory experiments. Scientists are recreating Hycean conditions in the lab, testing whether DMS can form abiotically under high-pressure, hydrogen-rich environments. These experiments will help us understand whether the K2-18b signal truly requires a biological explanation. The discovery has reignited interest in the search for technosignatures, evidence of advanced civilizations. If simple life is common on Hycean worlds, could some of these worlds host intelligent species? The City Institute has begun targeting red dwarf systems with radio telescopes, listening for signals that might indicate technological activity. K2-18b is more than a distant planet. It's a mirror reflecting our deepest questions back at us. Are we alone? Is life rare? Or is it woven into the fabric of the universe, emerging wherever conditions allow? This Hycean world, with its endless ocean and hydrogen skies, might hold the answer. The dimethyl sulfide detected in its atmosphere is a whisper, a faint signal across 120 light-years of space. But it speaks volumes. We're living in a pivotal moment. For the first time in human history, we have the tools to detect life beyond Earth. Not just imagine it, not just speculate, but actually find evidence. Whether K2-18b's DMS is biological or not, the fact that we're asking the question, that we're analyzing data from a world in another star system, is itself extraordinary. If this video opened your mind to the possibilities out there, hit that subscribe button. We're covering every major discovery as it happens, from exoplanets to black holes, from Mars rovers to the edge of the observable universe. This channel is your front row seat to the cosmos, and there's so much more coming. Next, we'll dive into the mystery of rogue planets, worlds without stars, drifting alone through the galaxy. You won't want to miss it. Thanks for watching, and keep looking up. This documentary is based on real scientific discoveries and peer-reviewed research, including observations from NASA's James Webb Space Telescope and studies published in the astrophysical journal Letters. However, it is important to note that the detection of dimethyl sulfide on K2-18b is preliminary and has not been independently confirmed. The content presented here is for educational and entertainment purposes, designed to inform and inspire curiosity about space exploration. For the latest updates, we recommend consulting official NASA sources and scientific publications.